Okay, so the next topic that we are going to talk about is effective nuclear charge. So in the effective nuclear charge, like I said initially before start of this lecture, this is very important topic. It's so important that unless you understand this topic pretty well, you cannot have good understanding of topics called anic radius, ionization energy, and electron affinity. Three important topics. So please pay attention and ask me questions when you see me in the class or during the office hours if you do not understand what is effective nuclear charges. So in simple words, an effective nuclear charge is uh, the attraction of the nucleus on the last or the outside of the electrons, like how powerful is the attraction of the nucleus on the outside electrons. So we have many different elements, like 118 elements. So these elements are arranged at a different distance from the nucleus that we are calling them as shells. Like for the nucleus, we said that it contains closest one is shell 1, next closest one is shell 2, next closest one is shell 3, but they were farther from each other. But nucleus is not going close to the shell 3, shell 4, shell 5, just goes farther from the nucleus, which means the force of this positive charge that is present in the nucleus is going to be different on the first shell compared to shell 2, compared to shell 3, compared to shell 4 and shell 5, just because they were farther. And also there are shells in between that are revolving around the nucleus that partially shield, because they go by paths like this, and when they go past the nucleus, it is blocking the interaction between the outside electron and the nucleus if a shell electrons goes past in between. So we are going to speak about that. One thing we are not doing in this chapter is calculating the shielding constant so that you can calculate the effective nuclear charge. It is not part of our lecture and it is not needed. Maybe in a future physical chemistry class, if you need to do that as a part of quantum chemistry topics, then you would do that. You can do that by using a rule called a Slatters rule. It's not complicated, but I just included the reference for you. If you want to explore how you calculate the effective nuclear charge and the shielding constant, you can do that by yourself. But all you need to know is there is a trend in the periodic table for the effective nuclear charge. So because in the periodic table, even across from left to right and from top to bottom, there is a trend. For example, from left to right, let me bring the periodic table again. From left to right, here you can see that hydrogen, for example, has 1 proton, but helium has 2 protons, okay? And from left to right, lithium has 3 protons, but beryllium has 4, boron has 5, carbon has 6, nitrogen has 7. The trend that we see is from left to right, they increase the atomic number by 1 because each element is going to have 1 more proton, okay? So there is a trend in the periodic table from left to right. And also there is a trend from top to bottom. So hydrogen has 1 proton because its atomic number is 1 here, but lithium has 3 protons, so it has atomic number 3. And because sodium has atomic number 11, it has 11 protons. The potassium has 19 protons because its atomic number is 19. So as you see, they were having more protons arranged by each element. It's a different number each time, sometimes similar number. Because they were having the large number of protons added consistently, you can say that there is a trend again. In the periodic table, as you go from top to bottom, you will have a more number of protons, and across the periodic table from left to right, you have at least 1 extra proton. So you can use that trend to predict that there is going to be a trend of the effective nuclear charge, Z effective, in the periodic table that you can correlate for the same period elements or the same group element from top to bottom or across. Before I show you these numbers and talk about these numbers here, Let me show you the formula that we use to calculate this Z effective, the nuclear charge. So you can calculate this Z effective if you have these two data. First data is easy to get. Z, basically, it is equal to number of protons of an element. So it is very easy to get. If you know the atomic number, you can get number of protons of that particular element. And this sigma, that is called a shielding constant, it is not complicated, but you need to do a little bit math to calculate sigma. Sometimes people want to refer it as the number of electrons, but that is false. Do not believe that, but it has a similar data, at least similar magnitude of number that you get, but there's going to be a little bit difference from electron numbers to the sigma. So shielding constant calculations is the most accurate, but using electron number is an inaccurate way of calculating the Z effective. So it is not number of electrons present. It is the shielding constant that you can only calculate from the defined values of the orbitals. Let me show you that. It is calculated by this famous rule called the Slatters Rule. Slatters Rule, and basically he proposed what is the shielding strength of a subshell that is present in a different shells. So he predicted that based on what shell an SRP is present, they have a different strength of shielding the positive charge of the nucleus reaching to the outside. So he grouped D and F orbitals together and S and P subshells together and gave a different unique strength of shielding constant, so that once you have the electronic configuration, you plug in the shielding constants to replace the completely filled subshell electronic configuration that eventually gives you a numerical number. Again, you do not have to calculate this. It is not part of our lecture. I'm just showing this by taking these slides from this open book textbook at this link. If you are interested, if you want to know how you get it, if you are personally interested, you're welcome to go to this link and look up the problems that are included. Pretty easy to follow, but just not part of our lecture discussion here. So basically, you can calculate the Z effective if you know the number of protons and if you know the shielding constant, which you can only calculate if you know the electronic configuration of an element. Then how much of S, P, D, and affect S, D subshells is going to shield the force of the positive charge reaching outside, then you can calculate that. But the difference between number of protons and shielding constant is going to be what called effective nuclear charge. Again, it is the effect of its positive charge nucleus from the nucleus to the last electron in the electronic configuration. So the trends in the periodic table is that from left to right, it increases. The left to right, it increases because that Slatters rule that I showed you just 2 slides ago, it gives the constant values to each shell, right? So if you have a completely filled shell, it will give you a certain value. They were for shells. Within a shell, you don't have a much difference of, you'll have a little bit of shielding between electron to electron of the same shell, but not as huge as a core shell. So a core shell will effectively shield electrons better than an electron in the same shell to another electron in the same shell. So that's why one common phenomena between all of these elements that you see here is all of these elements have similar type of core electrons, which are 1s2. Lithium has 3 protons, which means 3 electrons. Beryllium has 4, boron has 5, carbon has 6, nitrogen has 7, oxygen has 8, fluorine has 9. But all of these has only helium as their previous noble gas. So which means the core electrons of all of these elements is just 1s2, just one shell. However, as you increase the number of protons, we know that number of electrons are also increases. And because you are increasing more protons in the nucleus, but only just one core shell. Even for increasing the number of protons, these increased number of protons, for example, for fluorine compared to lithium, lithium with its 3 protons are only shielded by one shell for its outside one electron. However, for fluorine with its 9 protons in the nucleus are still only shielded by just one shell. Which means the nucleus of a fluorine is more effective in attracting its outside electrons to its much more closer, because they were just shielded lightly compared to lithium, which was shielded heavily because they are just 3 protons. So that is the trend, and here you can see that the Z effective is increasing from left to right as you are adding more protons for the same core electrons. So fluorine has the most Z effective. So we are going to use this trend a lot. So if not, it is stated clearly. Let me write it again. The Z effective in a periodic table. Let's see if this is hydrogen, the top left. From left to right, it increases. And from top to bottom, it increases. Yes. So this is the trend you need to know. And we are going to refer to this Z effective trends in the periodic table whenever I'm going to speak about ionization energy, electron affinity, and ionic radius. Okay. Before I move on, let me show you why it matters to know Z effective, right? So here on the right side of this slide, you are seeing an example of helium with its 2 electrons in its one shell, shell 1. So because there is a difference of Z effective on electrons depending on how many electrons present of an element, so removing first electron is, if you see this number, is easier compared to removing the second electron if the first electron is already removed. Because removing the first electron is easier because the other electron is trying to shield the Z effective from the another electron by crossing in between them. So removing first electron is easy because the other electron is always slightly shielded by this electron present. However, if that electron is already removed, first electron, in the case of second case, first case and second case, that electron is already removed. So all the power of the nucleus is just projected on the only presented single electron. So it is much harder to remove because there is no shielding that is present between the nucleus and that electron. There is no other electron to shield its Z effective charge. So the more Z effectivity is harder to remove, the less Z effectivity is easier to remove. Okay. So from